For Chapter 2, we're going to look about information related to light now. So we'll still be using the conversion ideas from Chapter E in Chapter 1, but now we'll be doing it with light instead of talking about mass nearly as much, which is our main focus in Chapter 1. So to start with, we need to be able to figure out how to determine properties of light based on other ones. So a lot of times when you look at light, you'll either know something at its frequency, its wavelength, or its energy. And from any of one of those, you can find any of the other properties. So for example, let's look at this first question here. Red light with a wavelength of 710 nanometers has what frequency? So first we need to recognize what it is we're actually looking for in this problem. Oh, there's my pin side. So we know that the wavelength is equal to 710 nanometers, and we know that we want to find the frequency. Remember, that's that new symbol. That's our question. So the equation we can use that relates these two is the fact that the speed of light, which is a constant that we know, is equal to wavelength times frequency. And we can rearrange this equation to say that frequency is equal to c over wavelength. I just divided by wavelength on both sides. And then we know that the speed of light that we're going to use is just 3.00 times 10 to the 8th meters per second. And if I want to plug this now into this equation here, you'll notice that this is in meters per second, but our wavelength is in nanometers. So we need to convert one of those so that those units will be able to cancel out. In this case, I'm going to choose to convert my wavelength from nanometers to meters, but you could convert your speed of light to meters to nanometers as well, and both would work out the same way. So we know that there are 10 to the 9th nanometers in 1 meter. And when we do that, our nanometers will cancel, we'll be left with meters, and we're going to get that we have a wavelength of 7.10 times 10 to the minus 7 meters. Now we're going to plug that into our frequency equation. We have frequency. That's supposed to look like a nu. There's a reason I type all of your exams. It's also kind of hard to write on this little tablet thingy. But we have 3.00 times 10 to the 8th meters per second. And we're going to divide that by 7.10 times 10 to the minus 7th meters. And here our meters will cancel. We can plug this into our calculator. There we go. And when we do that, we're going to get that we get 4.2 times 10 to the 14th, and I'm going to write this as hertz. Remember, this hertz here just stands for s minus 1, which can also be written as 1 over s. All of these units are the same, and you should recognize all of them so that you know, like in a multiple choice question, they're all the same thing. Now, this was going from wavelength to frequency. You can also go frequency to wavelength. So let's look at a question like that. What is the wavelength in nanometers of light with a frequency of 1.75 times 10 to the 10 hertz? So we're rearranging in this case that same equation because we know the frequency is 1.75 times 10 to the 10 hertz. We want to know wavelength. So this time when we have c equals wavelength times frequency, we'll solve for wavelength instead, which is equal to c over frequency. And here we're already in the right units since the speed of light is in meters per second and our frequency is in 1 over seconds. So it's still in the right units. We don't have to worry about converting at this step. So here we put in our 3.00 times 10 to the 8th meters per second. And then we're going to divide it by our frequency of 1.75 times 10 to the 10. And I'm going to write my hertz as 1 over seconds, so I see why they are indeed going to cancel. I can then plug these into my calculator. And when I do that, I'm going to get 0.0171 meters. Note that you want to make sure you're looking at your problem because if you answered this, you wouldn't get full credit because you hadn't finished the problem. The problem asked for the wavelength in nanometers. So now we do have to do a conversion. So 0.0171 meters. We're going to use our conversion that for every 1 meter, there are 10 to the 9th nanometers. And when we do that, we'll be able to do that multiplication. We should get that we have a wavelength of 1.71 times 10 to the 7th nanometers. This is also a good place to remind you that with some of the light problems, you're sometimes going to end up with answers that are very large or very small because we're talking at things like the length of a wave of light, and this time we're working in nanometers, or how many cycles light passes, or some other such thing. So it isn't always going to be like, oh, I should get an answer like 127 nanometers, and that's the only way it's right. Because sometimes students will see an answer like times 10 to the 7th and be like, wait, I must be wrong. Let me go change something. It's okay. That's always true that it can have answers like that, but especially in the light section, we're going to deal with very large and small numbers. So now that we've gone between frequency and wavelength, and wavelength and frequency, let's try doing another type of conversion. This time, we're going to be worried about energy, and in particular, we're going to have an energy pulse. It's going to be 2.47 microjoules. So let's write that down. So we have the energy, and this is our total energy of our whole pulse, is equal to 2.47 microjoules. That should be a J. We then know that the wavelength of this light is equal to 625 nanometers. And the question asks us, how many photons are there in this pulse? So initially that might seem like, wait, I don't have a single equation I can use for that. And you'd be right. The equation we primarily use in this course to determine energy is what the energy of a single photon is. So we can do that. And if we know the energy of one photon, we can find the energy of a bunch of photons. So let's start by finding the energy of just one photon. So I'm going to use the equation that the energy of our one photon is going to be equal to hc over wavelength. Remember that h is a constant as well. C is a constant, but c is in meters per second. So I'm going to want my wavelength into meters. And I'm going to go ahead and do that conversion on my own. I'm just going to put the answer here. It's done just like we did in the first problem, where we're using the 10 to the 9th nanometers in 1 meter. So we have 6.626 times 10 to the minus 34 joules times seconds for our Planck's constant. Our speed of light is still 3.00 times 10 to the 8th meters per second. Then we're going to divide it by our wavelength that we've done a conversion on. So when you do the conversion, you should get 6.25 times 10 to the minus 7th meters. Now we can plug all of this in for the energy of a singular photon. And we're going to get that our photon has an energy of 3.18 times 10 to the negative 19th joules. So this is the energy per photon. So remember, you can think of this as like this is going to be equal to the energy of one photon. So energy of one photon is this many joules. So what I want to know now is I want to take my 2.47 microjoules and I want to convert it from joules into number of photons. So to start this, I want to get it into joules so that I can use the information I got from that energy calculation. So I know there are 10 to the 6th microjoules in 1 joule. And from there, I know from my calculation that for every 3.18 times 10 to the minus 19th joules I get, I'm going to get 1 photon out. So I can figure out from that how many photons did I have in this total pulse. I'll put those both into my calculator. Now that I've done that, I will get that I have 7.77 times 10 to the 12th photons. And if you want to think of that with simpler numbers, if you're not sure why I divided by that thing, you can think of an example like this. Let's say I had a photon with a single joule of energy. Obviously, that's a whole lot. You're not going to have a photon with 1 joule more than likely. And I know that I have 25 joules total for my energy pulse. Well, that 1 joule can fit into that 25 joules 25 times. So I would need 25 photons to get myself from 1 joule up to the 25. I'm doing a similar thing here, but these are just numbers that you can't work with in your head. I'm figuring out how many times does this single photon fit into the total energy of my pulse. So that's the logic I'm using when I'm trying to rearrange this. There's not some exact equation that I'm going with for it. Now, we've done some calculations. Let's make sure we remind ourselves about quantum numbers. Note there are a lot of rules for these. You want to know your rules that regulate your N, your L, and your M sub L, as well as what those stand for. This is just one practice example to show you what they might be worded like. So for example here, we are told N equals 4 and L equals 2. And we are given 2 questions. First, we are asked, what are the possible values for M sub L? So in this case, my M sub L can be equal to negative L all the way to positive L, including 0, moving by integers. So that means my possible M sub L values would be negative 2, negative 1, 0, positive 1, positive 2. So these are my M sub L values that are possible, so I've answered the first question. My second question is, what type of orbital, S, P, D, or F, would this electron be in? And I know because the L is equal to 2 that I have to be in a D orbital. Remember that our L is going to tell us what orbital we have. So it's just as a reminder, we have L equals 0, L equals 1, L equals 2, and L equals 3 are the ones you're supposed to know. And they go S, P, D, F. So that's a way we can identify what type of orbital based on what our L quantum number is. Let's do one more example now, where this time we're going to work with an emission. So we've got one more math type problem to do. The question is how much energy is released if an excited hydrogen atom has an electron go from the n equals 3 energy level to the n equals 1. So here we know we want to calculate energy from different n values. So to do that, we can use our formula that delta E is equal to negative 2.18 times 10 to the minus 18 joules. And then in parentheses, that kind of looks like 1, we've got 1 over the final value squared minus 1 over the initial quantum number squared. Then for these we can plug in, I'll just write the whole thing. So once we plug in, we keep this negative 2.18 times 10 to the minus 18 joules. And our final n was just 1, so 1 over 1 squared is 1. But then we had 3 squared for our initial n, so 3 squared is 9. So we have 1 minus 1/9. We'll get 8/9 times this number here, and when we put that in our calculator, we will get, so negative 2.18 times 10 to the negative 18th times, we have 8/9. So from there, I will get a value of negative 1.94 times 10 to the minus 18 joules. And that's going to be the amount of energy that is released from our excited hydrogen atom. Note that if the problem had asked you something like how much energy would the photon have, you could also answer it in a positive form, since the energy is lost in our system where our excited hydrogen is going down, but the photon is gaining the energy. So I also, and even for this problem, because of how it is worded, I would have given credit for a positive or a negative answer, since you could think of the word excited implying the fact that this is a drop, or sorry, the word release, implying that there's a drop in energy, so that the negative was already included within the question. So I would accept either answer for this one. And just make sure to think about what your sign means, because that'll help when you have problems where you have to do this energy and then make some calculations on the photon. Since if I tried to put this into my something like my energy equals h nu equation, I would get a strange frequency that was negative, and we know we're not going to have a negative frequency for a photon. So that's the explanation of how to think about the unit. You also want to remember that while this problem had us calculate energy, it is also possible, and is indeed what you do in 2 of the homework problems, where you can have instead, you know the energy, and you're instead either missing this Ni thing here, or the final quantum state here. You could miss one of these two, and then you could solve for it by just rearranging your equation. So I know light can be a little bit challenging in some of the areas, but hopefully you can see that mostly you're using a couple of equations. You're using your speed of light equation, you're using an energy equation, either E equals h nu or E equals hc over wavelength. And then finally, you're using this energy calculation based on what your starting and ending state for your electron is for if you've got the n quantum number available. Other than that, there aren't a lot of equations you're applying in this section. There are just also some quantum number rules to learn. So while all these may look a little bit different and maybe you haven't seen them before, they're actually a very small set of ideas. If they're still giving you trouble, I highly recommend looking at the Chapter 2 section of the text. A lot of these equations and the information I'm mentioning are based on you having an understanding of conceptually what are we talking about when we talk about photons, when we're talking about quantum numbers. And by having a better understanding of the concept part, it can help with doing the math portions as well. Ideally, these problems are designed that it's not just about picking out one equation, putting some numbers in, but understanding where that comes from so that you can make adjustments as appropriate and you can know what things to use and really what your answer is about.